We are going to start off with Cambridge IGCSE Physics Paper 6, that is alternate to practical paper, and this is a tutorial for the students how we are going to solve this paper. Okay, let's start off with our first question, and it states that a student investigates the stretching of a spring. Figure 1.1 shows the setup, and you can see in this you have this figure 1.1 in which you have a meter rule, and then you have a spring and a clamp stand and a bench, and he's saying the value L naught is the length of the spring when L is 0. 0.0 Newton. The student measures the length L naught of the spring. She records L naught equals to 16 mm in the table 1.1, which is going to be shared later, I guess. Draw the diagram of the spring to show clearly the length L naught of the spring. So over here you have to draw the diagram of the spring that is going to be somewhat like this. Let's say this is your spring and this is the point, so this and this length is your, let's say this is your top, this is your bottom, and in between this is your L naught. Okay, moving to the next question. The student suspends a load L equals to 0.20 newtons from the spring. She records the new length L of the spring in the table 1.1. She repeats the procedure using load L equals to 0.4 newtons, 0.60 newtons, 0.8 and 1 Newton. The readings are shown in table 1.1. Calculate the extension of the spring for each load using equation E is equals to L minus L naught. So that is basically the extension formula. We got the value of E in table 1.1. So now we have to complete the table. So for the first value, if we use this, so this is going to be L minus L naught, which is the stretch length minus original length, which is going to be, for the first one it's going to be 16 minus 16, which is 0, and this is the answer. In the second one it's going to be 18 minus 16, which is going to be 2, so I will be writing 2 over here. And okay, you have to complete this table, so you have to put the units as well. So this is Newton, this is millimeter, and extension will be also in millimeters. Okay, so don't forget the units. Okay, now moving ahead, it's going to be 21 minus 16, and it's going to be 5, so this is going to 5 millimeters. 23 minus 16, and it's going to be 7. This is going to be 7. 24 minus 16, which is the original length, and this is going to be 8, and in the last it's going to be 26 minus 16, which is 10. So I will be putting 10 over here. So moving to the next question, plot a graph L on y-axis against extension E on x-axis and draw the best fit line. Okay, I will be drawing this, but I'll show you how this graph is going to be look alike. So if you plot again, it's stated in the question, so y-axis will be the load, and on the x-axis is going to be the extension. So I have labeled this, and if you plot the graphs, so the graph would be like this. This is your load, this is your extension. These values will be taken from the above, and it's going to be I'm plotting the values over. So this graph would be like this. If you plot these values from the this table again, and you must see this thing that I have drawn a red line over here. So basically draw the line that joins as many as possible points in the graph. So this is how it is going to be. Okay, so use the graph to determine EA, the extension produced by the load of 0.5 Newton. Show clearly on the graph how you obtain the necessary information. So basically what you need to do is, like, I'm going to change the color, it's going to be purple. So over here you have to see, this is going to be, let's suppose this is your 0 0.5 Newton, and then you have to go onto the graph and see this value. Basically you have to see this value what it is. So as per the marking scheme, it's going to be 5 mm, so I would be writing 5 mm over here. So this you have to do it by the help of graph. So in the next question, a student investigates the cooling of water. Figure 2.1 shows the setup, and the thermometer in the figure 2.2 shows the room temperature theta r at the beginning of the experiment. Record theta r. So if you do this, you can see this thing, the value of temperature over here. So it's going to be uh, 23, and don't forget the units. This is going to be degree Celsius. Okay, next question is, the student pours 200 centimeter cube of hot water into the beaker. He places the lid on the beaker. He places the thermometer in the hot water in the beaker. He records in the table 2.1 the temperature theta of the hot water at time equals to 0. He immediately starts a stopwatch. He continues recording the temperature in table 2.1 at 30 seconds interval until he has 7 sets of reading. Now complete the headings. This is going to be one marker. So this is time, which is going to be in seconds. This is theta, it's going to be in degree Celsius. Now he's saying the right time of the first column. So you see they're saying there is a 30-second interval. So first one we will start off with 0, 30 seconds, that is going to be 60, is going to be 90, 120 seconds, and 150. The last one is 180 seconds. So this is how you have to complete the table. Calculate the decrease in temperature delta theta between t equals to 0 and t equals to 180. So now over here what you need to do is that you have to find out the change in temperature between these two values when the time is 180 and when the time is 0. Okay, so if you do this thing, so it's going to be 92 minus 75, which is going to be 17. So it's going to be 17 degrees Celsius. Got it? Okay, calculate the average rate of cooling R of the water using the equation delta theta over delta T, where delta T is 180, include the unit. So now what you need to do is, you got the delta theta in your previous question, so that is going to be 70 divided by 180. So it's going to be 0.0944, and the unit will be again degree Celsius per seconds. Don't forget the units. A student states that the water cools slowly. Suggest two changes to experiment that the student makes to increase the rate of cooling of hot water without changing the starting temperature of the hot water. Room temperature remains constant. So first thing you can do is remove the lid or a cover. Remove the lid or cover, and you can use a thinner lid for beaker. I hope you got this. State one precaution that you would take to obtain accurate temperature reading. Explain briefly the reason for this precaution. Okay, for doing this thing, that you first need to do this thing, that you have to see or view the thermometer perpendicularly. Perpendicularly. And why you are doing this is because to avoid the parallax error. Avoid the parallax error. And you can also do this thing, that you can stir up the stir the water so that the temperature should be evenly distributed, evenly distribution of temperature, and you have to for wait for or wait until temperature stops rising. So you need to be careful about this. So obviously, when you are noting down the temperature by a thermometer, so you need to be very careful about these things, because if you don't see or view the thermometer perpendicularly, like if this is your thermometer, so the eye level should be like this. Okay, so this is the right way of looking at. If your eye level is like this, so this is going to be a parallel x error, that is wrong. So it should be like perpendicular, or you can say the reading should be at eye level. Okay, now moving to the next question. The student uses a measuring cylinder to measure 200 centimeter cube of water. He takes the reading, and from the bottom of the meniscus, explain the reason for taking the reading at the bottom of the meniscus rather than the top of the meniscus. Because there is a small difference between these two differences between these two meniscus. So that's why we need to take this. The student has taken this thing. A student investigates the refraction of light using semicircular transparent block. Figure 3.1 shows her ray trace sheets. Okay, and draw a normal NL through the center of AB. Okay, once you are doing this, so basically what you need to do is you have to put a scale between point A and B and find out the midpoint. Let's suppose this is your midpoint, and draw the normal. So once you have done this, so you can draw a normal like this. So this is going to be your NL, and we have to label this. Okay, this is done. Continue the normal so that it passes through the curved sides of the block, and label it NL. So we have done this thing, we have continued this thing till this is like this. Label the point C where the normal NL and AB crosses. So where it is this point, this is this point C. Okay, this I have already done. Draw a line DC below the line PC. Draw a line DC below the line PC at an angle of 20 degrees. Okay, so incident to the normal and the left of the, now you see the normal and to the left of the normal. So what you need to do is, if I change the color, so this is going to be like this. You need to take out your protector in order to make this angle. Okay, make sure you don't make a mistake. Okay, so you can use a D as well to make 20-degree over here. So this is also again done. Now moving to the next part, mark with the neat crosses X for the positions of two pins on the line DC. Okay, hold on, draw a line DC. So this is your D and this is C. Now you have to put two pins on a suitable distance apart from this ray of experiment. Label the position P1 and P2. So we can do this thing that we can put these pins over here as P1, and we can put another pin over here and we can mark it as P2 over here. Okay, we are done with this and we have done this as well. Okay, so now the next question is states that the student looks up from the position at the eye shown in figure 3.1, observes the image of P1 and P2 through the side AB of the block. So now you have to do this thing. She adjusts her line of sight until image P1, P2 appears one behind another. So this is what you need to be looking at. The image should be okay. So this line is going like this. You need to draw it with the scale. I'm drawing it with a freehand, so this is going to be how it's going to be refracted basically. She places two pin P3, P4. This is done. This is also done. The position P3 and P4 are shown in figure. Draw the line joining the position P4 and continue the line AB. Okay. We have already done on this thing. We have joined this point P3 and P4. This is P3 is pin 3, P4 is pin 4. The draw label E, the end of the line furthest from E. Now we have to draw this label E, the end of the furthest. Okay, so in this point that you have to furthest to AB, you have to draw the line like this. Okay, I'm drawing the line. You have to stretch the line P4 P3 till the end, and this is going to be this. And in your next part you have to put a D and measure this angle. Okay, so once you have done this, because it's saying an acute angle, so if you have done this, so you have to measure this, and this angle is going to be 33 degrees, which is your answer for theta. This is going to be your 33 degree. Okay, now state one precaution that students take to produce accurate rate trace. Okay, we can use number of precautions over here, so it's up to you how you are going to memorize this. First thing is this, that the pins should be verticals. Pins should be verticals, or you can say straight. Then it's going to be draw the thin lines. Draw thin lines, because if you do it with the uh, thicker lead, then you won't be able to get the right angle. And you can use a sharp pencil, use a sharp or mechanical pencil. So you can use any of these precautions over here. Okay, now the student replaces the transparent block of on the ray trace sheet in the position shown in the figure 3.2. Okay, now what we need to do is she replaces P1 P2 on the line DC in the same position used in A3. She observes the image P1 P2 through the curved surface of the block. She adjusts her line of sight until the image of P1 P2 appear one behind the other. She places two pins P5 P6 between her eyes and the block, so that P5 P6 and the image P1 P2 see through the block appear on one another. The position of P5 and P6 are shown in figure 3.2. Okay, let me check. Yes, P5 and P6 are over there. So draw a line joining the position P5 and P6. Continue the line to C. Label G the end of the line furthest from AB, and then you have to measure the angle alpha. So basically he is talking about first again you have to draw the normal line from the center. Again this is going to be like this. Just a second, I'll draw it again. This is your normal NL. I'll label it like this. Then we have to connect those lines like this, P5 and P6 like this. Again you need to do it with the scale. So now looking back the question again. So if you again put your D over here, or your protector, so this angle is going to be what, 69, and for this you have to subtract this angle 90 minus 69, which is going to be 21, and that is going to be the answer for your alpha, 21 degrees. Okay, so let me do one more thing, and this, I'm sorry, I have put this thing. Alpha is this one angle, this is going to be 69, and this is going to be the beta. This is going to be your beta, and this is going to be your alpha. And again you have to see this is Meyer thing and calculate the angle beta. So it's going to be 90 minus 69, which is going to be 21. And I forgot to put label G sign over here, so I can do this thing. So this is going to be GC, and this is done. Okay, the student suggests that the beta should be equal to the angle of incident. So what do you think? So now you see that over here, if I highlight this thing, beta is what? This is your beta, and angle of incident is what? In our previous question it was 20 degrees. So let me just show you, this is 20 degrees. So he is asking that there is another student who is suggesting that angle B should be equal to this thing, angle of incident I, which is obviously written over here as well. So you can compare these over here as well. So his suggestion is correct, because angle beta is not far from angle incident. Okay, so his suggestion is absolutely correct, but if there was a huge difference, so his suggestion would be wrong. Okay, moving to the next question, it states that a student investigates the change in current in a conducting liquid as the distance between two electrodes is changed. So I will be highlighting these things which is required. The circuit is shown in the figure 4.1. Plan an experiment to investigate the change in current in the liquid as the distance between the electrodes is changed. You should explain briefly how to do the investigation. We will go with the each bullet. So first of all, thing is this, that we need to find out the change in current in the liquid as the distance between the electrodes is changed. So initially it would be like this. The distance is, let's say, d1, then it's going to be, we are going to move further apart, and then it's going to be distance d2 and so on. So we will be, so we are going to first of all identify the independent variables which are going to be changed in our experiment, and that is going to be the distance between the electrodes. And then we are going to identify dependent variables. This is what we have to record, and that is going to be the current, because we are changing that current. And last we have a control variable which is going to be power supply. Okay, so the first thing is, let's explain briefly how to do the investigation. So when you're doing this, it's going to be like, first of all, what you need to do is you measure, put these headings in your data, so that you can do this question easily. So first of all, you measure the distance between two electrodes, then you record the current in the ammeter, because on changing the distance between electrodes, there will be change in the current in the readings, and then you have to repeat the readings for 3 times for 3 different distances between the electrodes. So this is done. State the key variables that are going to be kept constant. So this is going to be the size of electrodes and the volume of the liquid. Draw the table and columns to show how you display this. You are not required to enter the reading in the table, so this is going to be your table. Make sure you put the units over here, because if you don't do it, you won't be marked for that. Then it's going to be explain how you use reading to reach the conclusion. So you have to plot the graph. So you are going to be plotting the graph for this thing. So distance on one axis, and the amount of current that is changed is going to be on other axis. So this is it. Thank you very much.